everyone. I'm Siddharth here. Today I'm going to be talking about my project that I've done, my final year project, which is Advancing Green Cloud Computing, a machine learning framework for energy efficient task scheduling. So I would like to, before I start, I would like to thank Dr. Sudhakaran sir for being such a good mentor and a guide throughout the course of the last 4 months of implementing this project. Uh, now let's go ahead with this. So yeah, so why I chose this topic? This is because like when it comes to anything related to task scheduling and cloud computing, people always focus on the optimization when it comes to performance of the virtual machines or the network or the cloud, right? So it is when the word optimization is always directly correlated to the performance. So what I wanted to do is I wanted to highlight the fact that most times uh, the carbon emission or the environmental factors are disregarded. So energy consumption comes into play here. So if uh, like this project aims for sustainable practices in task scheduling by prioritizing total energy consumption and average energy consumption per task. We've taken these two uh, criteria or parameters as the key parameters in predicting the most efficient task scheduling algorithms. So yeah, the problem statement is it is speaks for itself, saying that rising energy consumptions are always prevalent in cloud services. So the need rises for efficient task scheduling to optimize resource use and minimize energy wastage. So we've used four different algorithms. We are focusing on four different algorithms: task scheduling. So first come first serve, shortest job first, round robin, and particle swarm optimization. So we are using these four algorithms. So the methodology. So what we do is we run each of these algorithms separately and generate a data set individually for all the four uh, uh, algorithms in CloudSim to using CloudSim software. And what we get is we get a data set for each of these. We get four different parameters. The resultant the result that we get from the data set is these four parameters. We get total energy consumption, average energy consumption per task, throughput, and make span. So what we do is we take the data set, individual data set, combine them, run them through a ML based model, and the we train the ML model to select the algorithm based on these four criterias, uh, and we judge these individual parameters like say for total energy consumption. If when taking total energy consumption as a key parameter, uh, how well does it predict the most efficient algorithm? So that is the performance evaluation. And like every other ML model, we can optimize it with progressive iterations. And in the end, by doing all this, we achieve green cloud computing by minimizing the energy consumption. So now let's go to the simulation parameter. So while as I said, while simulating this in the CloudSim software, we generated the data set was of the size like the combined data set was of the size 2000 rows and 17 columns. When all the data sets of the four algorithms were combined. And so we used a total of five virtual machines, which ran for 500 tasks or 500 iterations, with the machine capacity of 250 MIPS each. So when we simulate when we simulate one of the algorithms or run one of the algorithms in CloudSim, the features that we get is task length, start time, finish time, and waiting time of that respective algorithm. So let us look at the efficiency metrics. So make span efficient. So make span is essentially the total time it taken to complete a task or the execution time. So the goal is to minimize the execution time. So the algorithm with the least make span or execution time will be the most efficient. When make span is taken as a primary criteria for predicting the most efficient algorithm. So coming to throughput efficient. So uh, throughput is the number of tasks processed per unit time. So the more number of tasks are processed per unit time, more the efficient the algorithm is. So here the algorithm with the maximum throughput or maximum number of tasks completed per unit time is the most efficient and hence is called throughput efficient. When it comes to total energy consumption, the objective is to minimize total energy consumption. So the algorithm with the minimum total energy consumption is the most efficient, is termed most efficient. And again, coming to average energy consumption per task, it is very similar to the above case. We look for minimization only, and the algorithm with the least average energy consumption per task will be the most efficient, determined as most efficient. Okay. Now coming to the feature selection and neural network architecture. So before like progressing with the ML part, first we have to do feature engineering. So in feature engineering, here we have used a principal component analysis, where we have reduced the entire content of the data set to two principal components, and where two principal components contribute to more than half of the uh, contents of the data set, which reduces dimensionality, retaining only the critical information. So while doing this, a mean imputation is also done because there were a lot of missing data found. So which mean imputation addresses missing values with feature mean. And normalization is also done, which standardizes the features for equal contribution of PCA. So the coming to the neural network model, here we are using multi-layer perceptron, which is an artificial neural feed-forward neural network with two hidden layers. The first layer is 100 neurons, has 100 neurons, and the next one has 50 neurons. Then coming to the activation function, the ReLU layer, which is for efficiency and to avoid vanishing gradient problem. Uh, we have used an optimizer called ADAM, which is used for adaptive learning rate and effective convergence. Now coming to the results section, here we can see that when makespan is taken as a criteria, PSO has the least makespan, so hence PSO is the efficient algorithm when it comes to makespan. When it comes to throughput, again PSO is the winner as it has the highest number of tasks per hour. And coming to total energy consumption, again PSO is the winner at as PSO has minimal total energy consumption. Average energy consumption, when it comes to average energy consumption per task, PSO is again the winner as it has the minimum number of minimum average energy consumption per task. So now looking at the training loss uh, curve for makespan efficiency, that is loss versus epoch curve. So and the below curve for throughput efficiency. These curves show that this one is for TEC efficiency, that is total energy consumption, efficiency prediction, and the below one is training loss curve for AEC efficiency. Now, when you look at all these curves, there is an immediate uh, drop of the curve, and then it plateaus. So, what we can infer from these curves is that there is no uh, problem of overfitting in our data set. It gives us a good indication that our data set is good enough and trustable and reliable for performing prediction methods. So this is the classification output that we got. So as you can see, all the scores are pretty high. Let us focus on class one because that is the main predictor. So this is class one is when makespan efficient predicts the uh, algorithm with the least makespan. The throughput efficient produce determines one with the most efficient algorithm with the highest throughput, and so on and so forth for TEC and AEC respectively. So as you can see, these all are pretty high and gives a good indication that our prediction and uh, the fact that we have used TEC and AEC as parameters to judge the most efficient algorithm has not in any way disrupted the traditional trend of makespan or throughput. So the implications, as I said, they provide dynamic scheduling optimization, reduces carbon. This project helps in reducing carbon footprint in the cloud services and gives an insight into like the thinking that even energy minimization of energy consumption can also be used as a criteria uh, for like optimization of like technology. So when it comes to future explorations, we can use like even further task scheduling algorithms. We can diversify the algorithms, and we can expand machine learning and deep learning models for better prediction and robustness. We can expand and delve deeper into the nuances of efficiency metrics and see if there are even more nuances than energy consumption to consider when it comes to environmental improvement and minimization of carbon footprint, at the same time maintaining performance. And real world testing, only when we test this implementation in the real world, it will make more sense. So now coming to the next one, which is we have to focus on more renewable energy means, which aids in tailoring algorithms for renewable energy sources to support sustainable tech ecosystems. So to conclude whatever or summarize whatever we have said till now is the key findings of this project are like we've employed the MLP neural network to assess scheduling algorithms against key efficiency metrics, and we have achieved high accuracy in predicting makespan and throughput efficiency algorithm. That is, we have not this tells us that we have not disrupted the traditional way of judging and task scheduling algorithm. But now, when we introduced energy efficiency emphasis, uh, uh, like we'll see, we identified algorithm optimizing total energy consumption and average energy consumption per task. So this contributed to sustainable cloud computing with a focus on environmental sustainability. While at the same time, we did not, uh, give way or trade off for performance. So the training loss curves, as I said before, and the PCA validated the neural network architecture and feature selection respectively. Now let us go to the uh, now let us go to the code where I'll show you a little more deeper. So these are the four data sets for the respective algorithms individually. I've uploaded them and then uh, combined them, here, yeah, as you can see. And after combining them, I've added one extra column respectively for each. So totally four columns I've added for makespan efficient, throughput efficient, TEC efficient, and AEC efficient. So makespan efficient is something. So it defines an algorithm uh, which has minimum make span. So like whichever has the minimum make span is classified as 1, and the rest are classified as 0. So this is the binary aspect of it. They are binary values. All these columns have binary values. So when it comes to throughput efficient, whichever has the maximum throughput is termed 1, and the others are valued as 0. Similarly for TEC and AEC, whichever the ones with the minimum TEC and AEC values are determined as 1, and the others are determined as 0. So those are the columns, extra columns added. So once the data set is combined and this is done, uh, then normalization has to be performed in order to reduce bias. So once the data set is normalized, we find that there is missing values in the data set. So in order to you know uh, fill in the missing values, as the missing values may sometimes affect the end result, we introduce an imputer or imputing mean imputer, so which imputes average values of the respective column in the missing spaces. So the missing spaces are added with the average imputed mean. So then after imputation is done, principal component analysis is performed, where two components are considered. As you can see here, this is the graph we obtained from principal component analysis. So, and we get this variance ratio to be this 0.363 and 0.16. So what this tells us is that totally 0.52 when you add these two. So almost more than 50% or more than half. These two components contribute to more than half the features, so or the data set. So that is a pretty decent value to rely upon. So we've removed all the excess data and we are focusing on these two principal components alone, features. So now what we do is, once the PCA is performed, now we dive into the machine learning aspect. So we train our so we split the data set into training and testing part for makespan efficient. First we do it for makespan. We run the machine learning, create a machine learning model for makespan efficient. uh, so once we do that, this is the neural network model. We use MLP classifier, which has as explained, has two hidden layers, 150 neurons with an activation ReLU function and a optimizer called Adam. We run it for 500 iterations for a random state of 42. So, the random state ensures that every time a new iteration is done, our model stays consistent. So, it ensures that our model stays consistent for any random iteration or any random values. So once we run the prediction model, or once we run the ML model, the result that we get for makespan efficient is we get an accuracy of a solid 97%, which is great. Now, when we this is the loss epoch curve that we generated for makespan efficient, which is pretty decent and convincing. that there is our data set is good and there is no issue of overfitting. Similarly, when we do it for throughput efficient, we get an accuracy of 90, almost 99%, which is staggering and wonderful. And the graph again tells you the story that there is no overfitting, which is similar to the above. Now, when we run it for the our important feature or parameter that we introduce, which is total energy consumption, again the accuracy is almost close to 98%, which is amazing. We've achieved what we were trying to do, what we've achieved our goal of, considering energy consumption, minimal energy consumption as a criteria for prediction. Our accuracy is pretty decent, more than decent. And again, for average energy consumption per task, the uh, accuracy value is about 0.975. It's 97.5%, which is amazing again. So what I'm trying to say is, when it comes to technology, we should not restrict ourselves only to the performance. We can both the environmental aspect, the green we can, promote green technology, where technology and nature come hand in hand. So, improving technology doesn't mean destroying nature. We can focus more on minimizing energy consumption for a more sustainable and progressive world. So, thank you for listening to me patiently. That's it.